Okay, hello and welcome to Helsinki for the second briefing at the joint meeting of the Europlanet Science Congress and the American Astronomical Society's Division of Planetary Sciences. We've had a fantastic week here. It's been the largest ever meeting on planetary science that we've ever had in Europe. So we are very excited to hear what our panelists have to say today. I'm Anita Heward. I am the press officer for Europlanet. And I'm very grateful to my colleague Teddy Carretta from the DPS, who has been assisting us in putting together these press briefings. So without further ado, our panelists today will be talking about new discoveries from Juno, in particular those associated with auroras and auroral footprints from the Jovian moons. Our panelists today are Scott Bolton from the Southwest Research Institute, Alessandro Moirano from the University of Liège, and INAF, Vincent Hue from Aix-Marseille University, and Nicolas André from Supero. So, Scott, I will hand over to you. We will do questions at the end. If you have questions, drop them into the chat, and Callum will read them out.
Okay, well, so I'm Scott Bolton. Thank you for joining us for us to share some exciting news from Juno and some results. We go one slide. Oh, I'm supposed to do it. I forgot. Okay. Okay, so behind me you see an actual what Juno looks like, and next to Jupiter. And so this Juno is a kind of a special spacecraft in the sense it's quite large. It has 3 solar arrays. Each one are about 8.5 meters long each. There's at the end of one of those, you see it's a magnetometer boom there where we have magnetometers and some cameras on it. And then all the instruments, this spacecraft goes through space spinning twice per minute. So it's sort of like, imagine it cartwheeling through space. And each of the instruments kind of looks out, taking a turn, looking out between the solar arrays. So the instruments are outfitted that way. And it was launched in 2011 and arrived in 2016. And it's been orbiting there ever since. We're just about to do our 76th orbit this month. And of course, it's solar powered. And the unique orbit that is about Juno, which is that we go over the poles of Jupiter. So we're really the first spacecraft that goes over the poles as opposed to around the equator. Okay, so today's topic, as Anita mentioned, is aurora, and the aurora of Jupiter. And Jupiter is basically a monster planet in every way. It's like a planet on steroids. Everything about it is extreme, including its aurora. Its magnetosphere is very strong, and it's the largest object actually in the solar system. It stretches all the way back out to Saturn, and it's got very powerful aurora. Now, Earth and Saturn and other planets do have aurora, even Ganymede, but Jupiter's are special because they're so powerful. Generally, the aurora are these oval-shaped things like it is at the Earth. That process is driven a lot by the solar wind or internal magnetosphere processes, and the particles come in and precipitate into the atmosphere and make light when they collide with atmospheric particles. We're going to talk about a rather unique aspect of Jupiter's aurora, which we call footprints, which are that the footprints from the moons of Jupiter, the Galilean moons, actually show up on the aurora. And that's what the topic that we're going to be talking about today. And the way that works is the magnetic field is carrying all these charged particles in Jupiter, and it's spinning with Jupiter. It spins around every 10 hours. Jupiter's spinning, even though it's 10 times larger than the Earth, it spins 2.5 times faster. It's moving pretty quick to get around in 10 hours. It's day. The satellites, on the other hand, are moving around in a few days. Each one is a little bit different depending on the radius that away from Jupiter it is, but they're on the order of days. And so what's really happening is the magnetic field is spinning and crashing into the back of the satellite and moving forward. And as it goes through that, the magnetic field lines touch the satellite, and they connect that satellite or moon to Jupiter, almost like that magnetic field line serves as almost like a highway for the charged particles. They travel along that and they crash into the atmosphere of Jupiter and they make their own light. And we can see that when we look at aurora. This isn't brand new to Juno. We've seen this with the moon Io for a long time, and Europa and Ganymede. Nobody had ever seen it with Callisto, really. We were expecting it, but it was a very hard one to see. We're going to show you the first really capturing of that today. But that's kind of how this whole thing works. And so that I just wanted to give that introduction. So the next part of the introduction is just the orbit, so you can see how this works. This is a history of our orbits. The first one is called inbound to PJ1. We call those perijoves. So the first one, we came in over the north and we came out, went through and under the radiation belts and out the south. And so that's this first orbit right here. So you can see Juno was designed almost perfectly to study the aurora by the fact that we go right over the poles and we measure the particles that are going down into those aurora, but we also get great images and can do it. And we can actually see it both in the north and the south. We see the north coming in. Since we go out the south, we have a view of the south today. You'll see images of both the north and the south at different times. And then the orbit moves because Jupiter's oblate and kind of fatter in the middle than it is at the top vertically. And so its gravity field is not symmetric. So that twists our orbit around. So Jupiter is very powerful in its gravity field as well. And so what that does is it moves the closest approach, which is about 5,000 kilometers above the cloud tops, moves it north. We started out near the equator, and now we're moving more and more toward the north. That is what enabled our first extended mission, because as this perijove part, which is called here, starts moving north, the orbit is getting twisted around. And so when we're coming in, approaching Jupiter, we cross the equator closer and closer. And that's what enabled us to do our first extended mission, which we're just finishing up this month. We were able to go by the satellites. So we went close to Ganymede, then Europa, then Io. And we did science with those, and we looked at the particles even from there, even because we knew that they were also hitting Jupiter. Okay, so this is another close-up that shows you the real evolution of this perijove. And the main point of this is that as this orbit twists or gets changed, we actually get closer and closer to the pole. And so we're getting closer views of the pole now than we did when we started, because we're closer to it. Okay. Let me just, okay. So the next thing I wanted to show is just a little intro as to what you'll hear more about how aurora work from my colleagues. But here you see Juno's orbit and a couple of sketches. These are lines that are representing the magnetic field lines that these particles are flying in on. And there's both electrons and ions that produce this. And all aurora are done this way, but these field lines, if you can imagine, would connect to these satellites for a moment, and that's when you see this footprint. And they also get accelerated toward Jupiter, and a lot of the acceleration happens right above Jupiter, and so you see this. And so so that's basically now what we've seen in the history is we saw these moons all having these footprint, but we had never really seen Callisto with solid evidence. And the reason is there's a main oval on Jupiter, just like there is at Earth. And Callisto's orbit is pretty much where the field lines map out to that oval. So its footprint was inside the main oval, and so therefore it was very hard to see. We had a magical thing happen where some sort of storm pushed the magnetosphere and compressed everything, which happens occasionally both at Earth and at Jupiter. And so the aurora kind of move in closer. And when that happened, Callisto was left out in the wind, so to speak. And we just happened to be in the right spot. So you're going to get to see that. Okay, so I'm going to pass it to my first colleague here, Alessandro, who's going to show you. What you're going to hear from Alessandro is data from the infrared camera and spectrometer. We call it Jurum. It was built by Italy and contributed by the Italian Space Agency. And then Vincent will talk about the ultraviolet instruments results. And then finally, Nikolai will talk about the particles. So what you have on this panel is both two different sensors, right? UV and infrared, where we can see the aurora, and the particles that actually create the aurora. So you'll get kind of a full picture, whole story. Okay, with that, let me pass it on.
Thank you, Scott. So it's my duty to guide you through this more detailed introduction about aurora. So, as Scott introduced, Juno is orbiting around over the poles of Jupiter, and what you see on the right is what the infrared camera is able to record when Juno flies below the southern pole of Jupiter. You can see there is a big ring which we call the main oval. This is something that resembles, at least as a shape, the aurora at Earth. But there are also some features that we don't have at Earth, that is this so-called footprint, and those are caused by the presence of moon within the magnetosphere of Jupiter. Here you see a couple of examples. You have the Io footprint on top and the Ganymede footprint on the right. And those appears as bright, very bright spot that moves around the main emission of the aurora. So what is the root cause of this? Sorry. What is the root cause of this footprint of this auroral emission caused by the moons? Well, at Jupiter, we have a pretty unique celestial body, which is the moon of Io, because it's a very volcanically active moon that produces a lot of material that fills the magnetosphere of Jupiter. Most of this material is actually confined around the orbit of Io, and it moves around the planet faster than the orbits around the planet. So basically, Io is an obstacle, much like a bridge pylon that halts the flow of water. And this produces a local turbulence, and waves propagates along the magnetic field. The property of this of these waves changes as they travel from Io to Jupiter, and at some point above Jupiter's atmosphere, they can accelerate and drive particles, most notably electrons, into the atmosphere. And this triggers a chain of physical processes and chemical reactions that gives rise to emission of light at different wavelengths. If we now look closer to the footprints, we see that there is a pretty detailed structures, and we have a main bright spot, and this maps directly to their respective moons. But we also see that there is a chain, a tail of dots that we call subdots. And this is something that we didn't expect before sending Juno, but this is something that we observe consistently first at Io, and then also for the Europa and Ganymede footprint. And the discovery of these new features kind of triggered our analysis, because we wanted to explain what's going on. And the hypothesis we are exploring is that there is actually a feedback between the magnetosphere of Jupiter and the atmosphere. And this feedback kind of shape the morphology of the emission in this region of the footprint. Now, this would represent an important result for two main reasons. The first is, this is the first evidence that this would be first evidence that this process is observed on another planets than Earth. We know that this kind of feedback between atmosphere and magnetosphere shape the aurora at Earth, but also change how we see the aurora themselves, because you can think at the atmosphere like a photographic plate, and then you have a bombardment from the aurora that generates lights, and then you look at the lights to understand what's going on in the magnetosphere. But because we are kind of exploring the possibility of a feedback between these two environments, this means that we have to take into account that the two environments influence each other. So what happens in the atmosphere also has an effect of what happens in the magnetosphere. And the last, another important results that we got is that during particularly suitable condition, Juno can observe the atmosphere at limb. That is basically the instrument looks through the atmosphere, through the layers of the atmosphere. What you see here in the bottom image is the Jupiter surface, and then you see different layers of emission at different altitudes. Now, you know that Jupiter is a planet made of gas, so it doesn't have a hard surface like Earth. But like Earth, we define a surface level defined by pressure, and at Jupiter we do the same. So we kind of consider the surface of Jupiter a given pressure level. And what you see here, you see two different bright layer, one lower that is brighter, and this is caused by the presence of methane in Jupiter's atmosphere. And it looks so bright because you are looking from the side. If you look at the same pictures but from the top, the actual brightness of the methane is very low. And what you see on top is instead the Io footprint, but this time is seen from the side. And this gives us important information because by looking at the vertical distribution of emission, we have information about the energy that is deposited into the planet. Higher energy usually goes deeper into the atmosphere. But also you have information on the composition because the precipitation reacts with the atmosphere. So depending on where and which type of emission we see, we have information about the composition. And by that said, I think I can pass the ball to Vincent for the UV perspective.
Yeah, thank you, Alessandro. So yeah, Juno is also equipped with a UV instrument that captures ultraviolet aurora, a little bit like Hubble, except that we have very different geometry. We get very close from the planet, so we can have access to, in some case, extremely high details about the auroral structure. So first, I'd like to show an auroral movie captured by the Juno UVS instrument. This is a movie recorded over about 40 minutes period. And the blank part kind of corresponds to moments where Juno was not actually pointing at the aurora itself. So again, just as a reminder, those auroral emissions are created by charged particles precipitating, entering the atmosphere, exciting some molecules in the atmosphere, which then radiates. And this is what we capture with those UV instruments. As Alessandro and Scott discussed on Jupiter, so here we have a look at the southern aurora of Jupiter, characterized by the main oval, this kind of circularly shaped auroral emission ring. And around it, you can see the Io footprint, the Ganymede footprint, and the Europa footprint. Io is a very strong interaction because it's closer to the planet and sense more the magnetic field. Magnetic field is stronger at Io. And so we see this bright spot followed by a diffuse tail. And Ganymede is kind of mixed in with the main oval as well as Europa. So those are really hard to distinguish at times. And the way we distinguish them from the main oval is by looking how they drift around the aurora. You can imagine that the moon are orbiting around Jupiter, and therefore, since they're magnetically connected to those spots, you would see the drift related to the drift of those moons. And that's how we can distinguish if it's an aurora created by the moon or if it's not. So here today, we're really happy to report that we found the last missing signature of those 4 big moons of Jupiter, the one created by Callisto. It was really hard to distinguish because it allowed us to get very close to the planet and, as Scott mentioned, at the right time, at the right place. Let me explain a little bit more. So here on the left, you see kind of a global view of the magnetic field line connecting each moon to Jupiter ionosphere, to Jupiter high latitude region, both north and south. And on the right, you see kind of the image that allowed the Juno team member to make the discovery. This time we look at the northern aurora. We use a different color scale, which provides slightly more information. And on this one, we actually were very lucky to capture all 4 footprints of the 4 main moons of Jupiter. So let's take a closer look at this way, at the moment where we actually detected the Callisto footprint. So we're going to zoom in this specific spot. So here on the right, you see kind of the long exposure capture by the UV camera on Juno over several minutes of observation. And on the left, you see kind of the fine temporal resolution where we saw those actual spots drifting around. We were very lucky on this case because, as Scott mentioned, we had to have a specific event that would push the otherwise brighter background aurora away from the footprint of Callisto, which allowed Juno team member to discover that footprint. Based on the rotation rate of the spot and the region where we expect it to be, which is characterized here by this green line, the team member concluded that with no hesitation, that was the Callisto footprint. And you can see here, for instance, this was the time recorded at T initial time, 1 minute later, 3 minutes later, and so on. So not only Juno was able to provide observation with infrared, with UV, but also it went through the magnetic field line connecting the moon to the spots. And that's what Nicolas now is going to talk about.
Thank you, Vincent. So in addition to the auroral camera, Juno is also equipped with a magnetometer to measure the magnetic field of Jupiter and with some sophisticated plasma detectors, charged particle detectors. And I will report the measurements from those last instruments now. So before Juno, we knew that these auroral emissions are created by charged particles, namely electrons, that travel around Jupiter and that are guided along magnetic field lines towards the atmosphere of the planet. And this is what this conceptual sketch illustrates now. You can see the magnetic field line traced starting from the atmosphere of Jupiter and going outwards towards the location where the Galilean moons orbits. So the most equatorial auroral spot is mapped to the orbital position of Io. This is the moon that has the closest orbit to Jupiter. And then further out, you have this magnetic connection between the auroral spot of Europa and the Galilean moon, and also Ganymede and Callisto. So now, today with Juno, we were having for the first time the possibility to really witness this charged particle in action, to catch them when they precipitate along the magnetic lines towards the atmosphere of the planet and encounter the neutral component of the atmosphere and create this nice auroral emission. So here you see the trajectory of Juno passing by the key regions where those particles are accelerated and precipitate. And you see with this blue rectangular box, we have been able to measure their properties and confirm that each individual moon has different interaction with the atmosphere of Jupiter. If we take the case of Ganymede, we see that it has the largest interaction regions. The width is by far the largest. And this is because Ganymede has its own magnetic field. It has its own bubble around the moon created by this magnetic field. So it is a large interaction regions. If we go now to Io, we know that Io is the most active volcanic moon in the solar system. It creates lots of charged particles. And then this interaction regions is also very large, despite the small size of the moon Io. And then if we move to the other moons, we have Europa, which is the faintest interaction regions, because the moon is quite small and the field, the magnetic field in this environment is also small at distance from Jupiter. And then we have, for the first time, Callisto, where we were able, with one unique observations, to catch the electrons precipitating along the magnetic field lines connecting the moon to the atmosphere. And it has really a very nice and distinctive signatures in the charged particle observations. And this is now what I will try to show you. So remember this blue box where Juno cross and sees the particles in action. We will now fly with Juno. So imagine you are on board Juno. We fly in the magnetosphere of Jupiter. From left to right, time is running. So we are above the polar regions of the planet. We are in regions where you don't see any lots of particles. And then we crossed right in the middle for each of these plots, we cross a special regions, these interaction regions, quite localized, where we see particles. We see them with the color scale, you can see the intensity, the number of them entering the instrument. The interaction takes only a few seconds, so we need good instruments with good time resolution to catch this. Thanks to Juno, we can see, for example, at IO, we see a very intense signal, quite large, which correspond to those particles precipitating and creating the spot. Then at Europa also, but you see, this is a very small interaction region. At Ganymede, you have a large interaction regions because Ganymede has its own field. And then Callisto, for the first time we see here, small interaction region. And as mentioned by my colleagues, it was difficult to observe these interaction regions and the corresponding spot because it's right in the middle of this main oval at Jupiter where the main and the most intense auroral emissions are observed. With this unique case, you can see that this region is well separated from other regions where we see also charged particles. That's because this oval has moved, because something happened at a global scale on the magnetosphere of Jupiter due to its interaction with our sun. This is really a very original observations we are proud to report today to you. And this has strong implications also because we now have evidence that this process is universal at all Galilean moons. And we know that we are pretty sure that it also happens and occurs at other places in our solar system and possibly beyond with the connection, magnetic connection between exoplanets and their stars. So this is really a key result. And, with that, I'm giving back the floor to Scott to summarize.
So let me just kind of summarize or a little bit, put things into perspective. So, it's very interesting that we see this from all the Galilean moons, and I want you to think back a little bit. It kind of makes me reminisce of the idea and the story of Galileo, the scientist, of more than 400 years ago, pointing the first telescope up at Jupiter and discovering that we were not the only center, right? There was a center there. He saw stars, basically what they believed were stars, moving around this other object, and realized that this was a family, and that it was a planet with its moons, and in some sense, I wonder whether he imagined that planet, that family, was interacting with each other, and that's what we're really reporting on here. Very much that magnetic field, or that's creating that highway. It's almost like it's an umbilical cord that's connecting the mother planet with its satellites. And just for an instant, as the magnetic field sweeps by, different magnetic fields or different umbilical cords are quickly formed and connected and then let go, all happening every 10 hours. And so it's really an amazing thing. And I think Nicolas is right in the sense that this is an example. Jupiter, in many ways, is an example of what giant exoplanets must be like and how solar systems form. That's one of the reasons we created Juno, was to learn how important and how Jupiter affected and helped create our solar system. And in some sense, as we see this, I would expect that the same phenomena, since it works at all the satellites the same way, is universal, that out in the exoplanets and other solar systems where there's giant planets and moons, there are likely magnetic fields, and that those families are talking to each other as well. And I'll just point out that, what Alessandro showed from the infrared was very significant. Until Juno came along, we looked at these footprints like they were spots, single spots, and we didn't really know much about how it was worked. I mean, it was clear that it was a connection, but the physics of that connection really was beyond us. And when Durham, the infrared instrument, first saw these close up, it wasn't a spot. You saw in those images, it was like a ripple. And that really told us, oh, wow, there's a whole story here that needs to be investigated. And to find that same phenomena, when it first happened, people thought, I remember the conjecture in our team was well, maybe that's the Io Taurus and somehow it's affecting it, and Io special. Nobody immediately leapt to the idea that when we looked close at Europa and Ganymede, that we were going to see the exact same thing. And so that is, you know, a real hint as to how it must be working. With that, I think we'll take questions. If you have general questions, I can try to handle it, or I'll help point to the right person.
Thank you very much to all our panelists. That was absolutely fascinating. Do we have questions from people here in the room? Leo.
Thanks, Leo Enright with the Irish Television. I think this is for Nicolas André. The JUICE mission has a plasma wave instrument on board. There's a team from Dublin working on that instrument. So I'm interested to know, are there follow-up measurements that could be made at Ganymede to supplement the interesting kind of difference between Ganymede and the others in terms of the output? And I wonder, maybe does the Europa Clipper mission have some possible input into all of this?
So thank you for this question. So JUICE is also equipped with some camera and some detectors of particles and also of detectors of waves. So it has a very nice complement of instrument. When we will arrive at Jupiter and orbit the planet and later Ganymede, we will also look at these auroral spots, but from a different perspective. We will be a little closer to the place where the moons orbit at higher distance from the atmosphere of Jupiter, whereas with Juno we are really very close to the polar atmosphere, and that's the key to see these particles in action. But with JUICE, maybe since there is a connection between the atmosphere down to the Galilean moon, we will be able to sample different regions along the magnetic field lines where processes help to accelerate the particles. And so we will complement this observation, but from a different point of view. At Ganymede, interestingly, and Scott mentioned it, Ganymede has also its own auroral emissions. So it's a moon connected to Jupiter with an auroral spot related to Ganymede in the atmosphere of Jupiter. And at the other end of the magnetic field lines, you have some auroral emissions also in the small atmosphere of this moon. So it will be very spectacular to look at this connection in a few years.
Yeah, I mean, I'll just echo that and say that you know, JUICE won't reproduce exactly. That's the beauty of having the multiple spacecraft all in different orbits, is they complement each other. And so we really are designed, and almost perfectly designed, in order to look at this at one end of that umbilical cord, the one that's connected to Jupiter. We did fly by Ganymede close, but we only got one flyby. JUICE, on the other hand, is going to really investigate that other end of that umbilical cord, right? And so that's really going to be great, because if you can anchor the physics on both sides, right, and what's going on, you really get a much better understanding of what's happening. So I believe it's going to be fundamentally important what you're going to get. And the plasma wave instrument that you mentioned is a very important one. We have a plasma wave instrument as well. And they're very important because that's how nature moves the energy between the particles, and when things are out of balance, that's really what comes out. It's a very important tool to understand how nature deals with energy imbalances and things that are out of whack. And of course, out of whack means great aurora. You know, when things are out of balance, you're having energy exchange, and that's when you get great light shows.
Of course you can.
Just a quick follow-up. The two missions that are on their way to Jupiter, they don't get there till kind of the beginning of the next decade. Will you still be operating? Do you envisage that there might be opportunities to do simultaneous measurements with all three spacecraft?
That is possible, although it's you know, it's a little early to plan that. we're waiting. We've put in a 3-year extension, and we're waiting to find out the results of that. But even with the 3 years, that won't reach all the way to the time that these arrive. It is conceivable that we would be surviving and still working at that time. It's many years in the future. And as you, if you know from the orbits I showed, Juno gets a lot more radiation every orbit. So the whole question is will everything be operational that long? And do we continue to get funded all the way through? But it is possible. And if you could get 3 spacecraft in the same system, all looking at different things, that would be really exciting.
Thank you. Do we have any questions online? No. Okay.
Hi, Camille Carlisle, Sky and Telescope. I have a small question and then a more detailed one. If you could go back a couple slides to where we showed the little blue, the thicknesses. Yeah. Distance-wise, how wide are the highways where you flew through?
Jupiter is huge, as you may know. And so these interaction regions, they are also they have also a size which is between 100 and a few thousands of kilometers. So
Okay. My second question is, could you go into more detail about how you see this feedback process working that creates this tail of hotspots? I'm not sure how I should envision this.
So it's indeed quite complicated. It took a few years even to just wrap my head around that, and I'm still not sure if I got something definitive and something we are exploring. But the idea is that all this interaction between the planet and the moons involves, Scott says, waves and electric currents. So the idea is that this mutual feedback basically shapes the currents and funnel the waves in specific locations. This is a very, let's say, qualitative explanation. There are models, indeed, mostly developed for Earth, and then we try to apply it as order of magnitude estimates to Jupiter so far. That kind of shows that depending on the direction of the waves and the intensity of electric fields in the magnetosphere, you could this interaction between moons and planets can give rise to such formations. But in a nutshell, it affects the shapes and the location where the currents and waves passes.
Okay, so maybe it's like, if I think of a multi-lane highway, it affects how wide the highway is, that there might be outer lanes that are hitting different places.
You can think like a highway. You have a chaotic chaos uniform, and then you go through a toll, and then you need to funnel the cars, but you have places where the cars are and places where there is the toll, and so you cannot have a car passing by there. And then you have the atmosphere right after the toll.
Okay, and so the interaction determines which lanes are open.
Yes.
Okay. Thank you.
Great analogy. So let me just point out also that this figure is the purpose of this figure was conceptual, right? Not to exact highway location. But the point here we're trying to make is that Juno is passing through very close to Jupiter on these field lines. And so you see the acceleration. Now we're in polar orbit, so there are times when we're going through these field lines from much further away, and maybe it would be just really, a needle in a haystack that you got on a field line that was connected, and the signature might not be as strong because you're not under the acceleration region. And so the real trick is that this highway or umbilical cord goes all the way to the moon, and the particles are moving all the way along back and forth, right? They may not get accelerated till right above Jupiter, but the connection is there. And so Io, for example, is 5 Jovian radii away. Europa is almost 10 Jovian radii. Ganymede's more. So each one. So these are quite long distances these field lines are traveling. And the particles are moving, they're coming from the moon all the way in. But one of the key pieces is how big was that region, because there's also an acceleration. and also how big is the footprint or this width. The easiest one to understand to me is Ganymede, because it's a magnetosphere. So like our magnetosphere, there's a balloon around the moon itself, so the moon appears larger. So the whole interaction region's larger. I don't know if that helped, but.
Thank you. Any questions online? No. Okay. Roland.
On the BBC. Could you just go to Nicola, to the next slide that you had? Okay. So just out of interest, I'm not quite sure what the vertical axis is on that.
So it's what we called energy time spectrogram. So from left to right, you have the time running. And on the vertical scale, it's the energy of the particles we measure.
And then the color is the number.
Yeah,
Yeah.
exactly.
Okay, that's brilliant. I don't know if this is the right way to put the question. Can you associate with those bits where you're going across the roads the current or the energy that's being delivered? I'm just wondering, you know, you're talking megaamps or megawatts or gigawatts or something that's being delivered. I'm just trying to get some sense of how energetic the process is.
Yeah, I think the current strength is on the order of mega amps, if I remember correctly. Maybe Alessandro knows better that, but it's on the order of few mega amps, if I remember correctly.
The point is also, depending on who you ask, you get different answer, because some people look at the particles and the particles carry some energy, then it's deposited into the atmosphere. And if you look at the infrared, there is a fraction of energy that is converted into infrared and another fraction that is converted into UV. So it depends a little bit of who you ask the question. So in terms of currents, I think we are in the order of mega amperes. I think in terms of radiated power is of the order of gigawatts, I think. So just as order of magnitudes. Yes.
Yeah.
As Scott was saying, this is a planet on steroids.
But I often think of it in the terms of currents, because it's like an engine, this thing. You know, this magnetosphere is whipping around with a lot of charged particles. So it is, you know, it is like an engine, and it's putting out a lot of power. And there's a lot of power available to in this system. And so we're seeing some of this being distributed. But he's right, because if you look at light, you're looking at it, you know, in one kind of energy unit, and then you look at currents, and that's a different one. It's a very bright light bulb.
Thank you. Do we have any more questions?
This might be an unfair question, but what you just said made me wonder, could we ever find a way to tap into the magnetosphere to power our spacecraft instead of relying on solar panels?
So I think there were some experiments like that where they strung along wires or something to get potentials across, and see if you could get, you know, reap some power. I don't think that's done very much. One is it might not be a reliable way to do it, because it's very variable, and where you go, it's going to change. And of course, when you create that potential across something in a spacecraft, you could short the whole thing out, right? I mean, it's sort of like saying, you know, I mean, I'm not, you know, saying anything negative. I think we should explore all energy sources that we can. And the magnetosphere is sort of an untapped one, maybe wisely, because it's sort of like you could look at geothermal sources and say, oh, why don't I tap a volcano and power things? And there's probably reasons not to try that. So
Fair enough.
Thank you.
You know, if I could just ask a question about poor Amalthea. One of your early slides was really quite dramatic, showing, you know, the various PJs and the flybys. And she's sort of sitting over on the right all alone. And she seems to be always the bridesmaid, never the bride. I just wondered, is there any, has there been or will there be any opportunity to image Amalthea? I mean, it is the biggest moon of Jupiter after the Galilean satellites.
It is. It's a very important moon. It's not alone either. There's a family of moons in there. Amalthea is by far the largest of that family of what we call inner moons. But there's a number of them. They're embedded and sort of mixed in with the rings in these high radiation belts. So I never forget about it because it's in a very dangerous area, you know, a hazardous area. So if we are able to hear from NASA that we go on with the second extended mission, we will have opportunities to fly by some of those moons at various distances during this next second phase. That decision hasn't been made yet, but there is an opportunity to go in there and study it, and it's not. This is virtually an unexplored area because it's so hard to visit, and so Juno is very much designed like an armored tank. And so if there is a spacecraft that's going to be able to survive in something like that, it would have to be something like Juno. And, you know, so the opportunity is there. And we can only hope that we're able to survive and that NASA is able to fund that part of the mission.
Right. I think we are almost at the end of our time. So unless anybody else has anything else pressing that they'd like to ask, I'd like to thank all of the panel and thank all of the journalists who are here in person and maybe watching online as well. It's been a fantastic meeting so far. We're not done yet. We've still got a day and a half to go. Next year, EPSC will be in Den Haag in the Netherlands, and we hope to see you then. But in the meantime, a round of applause for our panelists. Thank you very much.